Hello and welcome to today's Friday Transportation Seminar. My name is Aaron Golub and I will be introducing and moderating today's seminar. Our Friday Transportation Seminars have been a tradition since the year 2000. These seminars are once again being held live here at Portland State University's urban campus, located on the ancestral homelands of the Multnomah, Cathlamet, Clackamas, Tumwater, Watlawa, and Chinook bands of the Chinook, the Tualatin, Kalapuya, and many other indigenous nations of the Columbia River. It's important to acknowledge that we are here because of the sacrifices forced on the indigenous ancestors of this place, remember these communities, and honor their lives, legacies, and descendants. Today, we are pleased to have David Young present on system-level risk management of transportation structures and networks. David Young is an assistant professor here in this structural engineering in the Department of Civil and Environmental Engineering here at Portland State University. His research focuses on structural reliability and risk-informed decision-making for infrastructure systems. His recent work specializes in unifying risk and resilience assessment in multi-hazard scenarios, devising novel machine learning techniques for infrastructure management and risk-informed infrastructure adaptation to climate change. He is the recipient of the 2022 Moisif Award from the American Society of Civil Engineers. He's the author of 29 journal papers, 3 book chapters, and over 10 contributions to various national and international conferences. Before we begin, here's a preview of the remaining speakers for the fall series. As an overview of today's seminar, you can expect our speaker to speak for about 40 minutes, followed by Q&A. We will be receiving questions through the Q&A feature on your control panel, and we'll ask them at the end of the presentation. If we run out of time for all your questions, we will give our speakers the opportunity to email written responses for any questions left unanswered. We have enabled closed captioning, but you must click on the CC feature on your control panel to view them. We will be recording today's webinar. It will be available on our website later today, along with the presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. With that, I'll hand it over to David.
Thank you. Thank you for the introduction. My name is David Yang. I'm the assistant professor of structural engineering at civil and environmental engineering here at PSU. So today I'm going to talk about a summary of my research focusing on the system level risk management for transportation structures, especially at the system level, talking about transportation networks. So first of all, thank you everyone who showed up today in person. It's not the best weather to travel, I guess. So thank you. And thank you for the invitation. Let me see. Oh, I think I got this. So first, before we actually talk about risk management, I do want to kind of make sure that we are on the same page. That is, how do we define risk? So basically here, risk is defined as the simple relation between the probability of a hazard as well as the consequences of that hazard, so the extent of impact. Okay, so the probability of a hazard event will deal with the likelihood of that hazard as well as the exposure to our civil structures. So this is traditionally the domain of structural engineers. So we talk about how to evaluate from a probabilistic sense what is the likelihood of structural failure or the likelihood of structures in different type of damages. So one of the hazards that is of relevance to us is that Cascadia subduction zone. There are various colleagues in our department working on either the hazard characterization or the structural vulnerability analysis under that hazard event. So considering we are here for a transportation seminar, so my talk today will focus on the second part of risk assessment, that is the consequences of the failure. So specifically, the consequences could be economic. So that is how much money you need to repair, rebuild, rehabilitate a structure that fails. It could be also social consequences. Here, we can talk about what will be probably fatalities, what will be the extra travel cost, travel distances, emissions for all those actual travel that you need to conduct due to a structural failure or structural maintenance. So those also could be tied to the environmental consequences as well. So the figure here shows some of the failure consequences under hazard. So one is from a natural hazard in the recent earthquake in Taiwan. The other one is also a recent structural collapse in Pennsylvania near Pittsburgh due to the lack of attention for structural maintenance. So we see that there are a lot of social consequences attached to the failure and damage of civil and transportation structures. So also what we are looking at today is going to be not only isolated for a single structure. So here, this is based on the fact that we know as a transportation network, all the assets are interconnected. So the failure at one infrastructure asset, for example, a key bridge, will have a dramatic impact that propagates through the entire transportation network. So for example, here, this is the aerial view of the river crossing bridges here near downtown Portland. And you can see this is a kind of a typical Monday afternoon rush hour travel pattern. So as you can imagine, if one of those bridges has some service disruption, there will be some consequence here in this traffic time for all the travelers within the city and across the cities as well. So this will be the focus, the scope of this talk. So how do we first quantify, assess this risk at the transportation network level, and how do we improve our transportation systems so that this risk can be minimized? So first of all, traditionally, this risk assessment in Denver was usually carried out, at least for civil structures, at the asset management level. So this has been traditionally how, say, Department of Transportation has been managing and analyzing the potential risk. So this type of risk assessment approach is based on the fact or based on the assumption that network performance, so that means the travel time in the transportation network, for example, can be reasonably approximated by aggregating all the asset level performances. So basically you see how many travelers is going through one bridge and then use that as a surrogate for the bridge performance for the transportation performance for that bridge, and then you add that potential risk to these impacted users across all the bridges in your stock. So that will be how you evaluate the societal risk at the asset level and translate that to network level. However, as I mentioned before, so the transportation assets are actually interconnected. So here I'm showing a specific like a toy example to illustrate this point in a more quantified way. So suppose you have this very simplistic transportation network from the origin A to the destination B. So originally, if nothing is happening to your transportation structures, so you have some traffic on each of the possible links. So we assume that in the middle link, there is a bridge. So traditionally, what people do is, as I mentioned before, if there is a failure event on this link or on this bridge, so there may be some local detour that you can take. So since it doesn't consider any network effects, what it assumes that what's the assumption is, so the traffic pattern will not change despite the failure or service disruption at this bridge. So it will still consider like 1/3 of the traffic demand from A to B will choose the first link and second link and third link. And the social impact will only affect the users on this middle link who will choose that from A to B using that second link in the original intact network. However, in reality, this is not necessarily the case if actually this bridge fails and people has to choose a detour URL through a local road with a smaller capacity. So what people actually will do is they will actually choose the other route with faster travel speed or faster travel time. So what you see is not only the traffic time on this damaged link will be compromised, but so because of people choose the other routes, the travel time on those links will also be impacted. So they will impact the other users who originally also use the top and bottom links. So this is a kind of intuitive view of why this traditional way of doing risk assessment by aggregating asset level performance may not be the best way to evaluate the transportation network risk. So what type of what type of performance level we will usually talk about in a transportation network? So this will include connectivity. So this type of performance will try to see how many independent links connecting one origin and the, one destination, and then you count those across all the origin destination pairs. The other type is a slightly more complex, talking about the capacity side of the transportation network. So here you may be interested in the maximum capacity from an origin to the destination, whether it be commerce or it is freight or it's just commuters. So the third type is considering both the capacity side of the network as well as the demand side of the network. So not only do we consider what is the capacity from origin to destination a network can carry, but also given the traffic demand of people moving from an origin to a destination, how those people will choose their preferred route to achieve their trips. So computationally, from connectivity to travel time, you need more and more information in order to do the analysis. And also, there will be more complex algorithms involved in order to quantify those network performances. So we will come back to this three type of performance measures later on when we are trying to actually do network level risk assessment. But these are the three things when you do risk assessment at the network level. Those are the three indicators that you can use to see what is the transportation network risk and a hazard. So why does it matter to do a risk assessment? So the risk assessment is important is because it has some indications for infrastructure management. So specifically, risk is usually defined as some type of benefit. If you do a bridge improvement work, so that will reduce the risk of that bridge fails, right? So the difference of that risk will form the benefit of your project. Of course, no project will be free, so there will be a cost for that project. So for each this project, you will have value. You will also have cost of that action. So you for a risk manager or for infrastructure manager, what they a lot of time want to do is to find the best set of projects that they want to do in order to maximize the total benefit, whether it's only agency benefit in terms of risk reduction or both agency and societal benefits. Okay, so this is usually in operations research formulated in sometimes in a knapsack problem. So essentially, this will be the way that you can choose which project I need to do by comparing and ranking what is the benefit to cost ratio of different projects. So rather than doing kind of really involved optimization problem, you can just rank all the projects in terms of benefit and cost, and then choose what are the best way to move forward to improve your infrastructure system, meaning to reduce the risk. Okay, so accurate risk assessment is accurate in that aspect. So it will directly tied to how projects are ranked and selected and those kind of things. And another thing why risk assessment should be in the picture of people's mind is some of the current conditions for our infrastructure, especially transportation infrastructure. So first of all, we have a massive amount of deficit structures. So the latest report card from ASCE states about 7.5% of the Soviet bridges are structurally deficient. So this translates to a lot of travels every day. So there are a lot of travels going through this structurally deficient bridges. It's also an international phenomena. So this is a slightly older report from Institute of Civil Engineers from that's probably the ASC equivalent from UK, stating that 1/3 of the local transportation system need maintenance. We have a huge amount of deficient bridges, but we also have a limited amount of resources, either environmental resources or financial resources. So 60% globally, based on the latest McKinsey, not the latest, recent McKinsey report. The same report card states about 123 billion in backlog. Okay, so those are the realities we are facing. But on the other hand, for a lot of the agencies, they don't have a very consistent and objective of allocate the limited resources. So find a better way to quantify your risk, and risk-based benefits will improve this situation. So that's why another aspect of why it matters. And so that's the national and international situation. So this slide shows the local situation here for in the state of Oregon. So based on the 2021 bridge condition report in the state of Oregon, so based on the current bridge replacement rate, meaning how many percentage-wise bridges will be repaired every year. So the estimate is a bridge should have to stay in service for over 900 years before it's turn to be repaired. The design service life for the bridges nowadays is 75 years. So there is a huge discrepancy there. So that means a lot of the resources have to put into sensible maintenance actions in order to kind of keep our infrastructure system safe. So those are some of the backgrounds and motivations and kind of why this type of research matters in reality. So the first thing that I want to introduce is to demonstrate through a research what's the difference between a project level risk assessment that is traditionally has been conducted by the agency and a network level risk assessment, and how those will impact the ranking of different bridges. As I mentioned before, the ranking will have an implication on what type of projects should be selected. So yeah, and this part of research was published in SC Journal of Infrastructure Systems. So here's a brief overview of methodology of this study that has been conducted. So here we have built a deterioration model through using Markov chain. So because if I'm trying to design maintenance actions or evaluate the risk of deteriorated structures, we first need to know how the structure deteriorates. So the second thing, as I mentioned before, is to use the travel time within the network to evaluate the risk and compare that with the risk-based ranking using some other performance indicators. So this slide basically shows the building of a Markov deterioration model, where so the infrastructure condition, in this case, the bridge condition, is quantified by from 0 to 9 condition ratings. So this is based on the federal highway protocols. And to model deterioration, we use this Markov model where assumes that there in each year there is a probability a structure will stay in the current condition rating, and there is another probability that will deteriorate into the next worse condition rating. So this is a simple mathematical model just to see at the bridge network level, a lot of structures, how this will deteriorate manifested by the condition ratings. And to get those transition probabilities that you see from the previous slide, so we leveraged the national bridge inventory data, where you have the transition probabilities from at least, you have the transition frequencies from one condition rating to another condition rating from at least the year of 1993. The data starts from 1992, but in order to know transition, you need to know what's happening in the next year. So with that, you can then kind of have an estimate of what will be the probability of a structure transition moves from one condition rating to another condition rating. So this figure shows this statistics based on the California bridges and looks at the frequencies of transitioning from condition 7 to condition rating 6. And with those transition probabilities, you will be able to then predict how the infrastructure deteriorates. So the figure here shows the condition rating deterioration over time for a bridge superstructure that usually include the bridge girders that is carrying the bridge deck. Here, the second figure here shows how the infrastructure, how the substructure will deteriorate. So substructure, usually those are bridge piers, so the band, anything that is carrying that superstructure. So here, different shade of gray represents the different condition ratings. The lighter it is, the better the condition. And what we can see is over time, the better rating will decrease and the worst condition will increase. The probability of, or the percentage of worst condition will increase. So what we did here is, again, recall that for risk assessment, we need not only the consequence, but also the probability. So here, what developed is a simple relation that translates the Markov state, or you can imagine this is at the condition rating of a structure to the structural reliability index, which will be the indicator of how likely a structure fails. So those are from just structural reliability theories that I will not dive too deep into. So let's see some of the results. So we use this network level risk assessment. So to illustrative transportation network. So the purpose is to showcase what will be the top 10 bridges in terms of their bridge ranking, and what will be the impact of those bridge rankings based on different performance indicators and risk indicators. So here we are analyzing this transportation network. This is a highway transportation network in the county of Los Angeles, where we have 91 highway bridges with 66 lanes. And the flowchart here is a kind of summary of this methodology that I briefly touched upon. So essentially, we are using the National Bridge Inventory data, which gave you all the condition ratings and the time series of those condition ratings. So we know how bridge deteriorates and how likely they are going to fail. And we have the GIS data of this interested region so that we can build the transportation network. And we have also the census data within this county, so we can know what is the traffic demand from different neighborhood. So with that traffic demand, with this network model, then I can assign the traffic flow to different links to know that what will be the traffic pattern, typical traffic pattern within this highway network. So another thing that, as I mentioned before, is the indicators we're using for the risk assessment. So we are comparing different indicators to showcase why it is important to rank bridges based on their network level risk. So the first indicator that we are following is the structural adequacy and safety. So you can consider this only as the likelihood of failure of an asset. Okay, so this doesn't consider any consequence of a structural failure. The second indicated sufficiency rating. So this does consider both the current likelihood of structural failure as well as the consequence of that failure. However, so this is a so-called qualitative indicator where essentially this is from an expert panel saying that what will be the importance, different weights of failure probabilities and failure consequences, and I come up with a sufficiency indicator qualitatively to represent the risk of a structure. Of course, you can do quantitative risk assessment, as I mentioned before. So what's the difference here is you do measure the agency and societal risk quantitatively, but you only consider those risks at the asset level, at the project level. So you don't really consider when the bridge fails, how the traffic will reroutes around that failed bridge. So you only consider, okay, all the users will still choose that still old route with some local detours. The last one is the one that we're interested in, that is this network level risk assessment. And so this is the results of the traffic assignment. So based on this, we can then evaluate what is the top 10 bridges based on these different indicators that I just introduced before. So the takeaway here is different indicators do give you very different bridge rankings. So the safety and sufficiency rankings sometimes may overlap, but it differs very much from the top 10 bridges based on ranked based on the network risk that we mentioned before. And this is a more quantitative view of how the bridges will be ranked. So the orange bar will be the risk ranked based on the quantitative project level risk. And then the blue one will be those based on the network risk. So the indication of this, if you recall the previous slide, if you are trying to assign resources for different bridges, if you rank the bridges based on the project risk, you will consider the first bridge as the most important, and then this bridge as the second important. So that will result in some misallocation of resources. So that's why this type of risk level, network level risk assessment is important. Okay, the second thing is, so that's risk ranking, risk-based ranking. This is how we can actually do asset management considering a stock of bridges. So this is achieved by this concept called deep reinforcement learning that I will later on elaborate. So this is from these two studies we published in the SC journals. So a little bit recap here. So we have the risk at network level. So now we know that this is important. And then these are the three types of performance indicators that we can use: connectivity, capacity, and the mobility for the transportation users. So here we choose this capacity of the network because that's a sweet middle ground for a network level analysis that is not that difficult to compute, but also reflect a network level functionality. And network risk then can be formulated by the difference of the network capacity of a damaged network and an intact network. So I will move a little bit quicker considering the time. So here, so if that's the risk, so what's the risk management process in the life cycle of transportation, in the service life of the transportation networks? So consider you have a transportation network. So this is a so-called sequential decision-making process in the sense that at each time of decision-making, a decision maker or decision-making tool needs to decide from a wide array of options, maintenance options. And then, excuse me, so those options will have different cost and risks as well. So they will choose from a wide array of actions that they can take, either it's inspection or repair, and then implement those into the different assets in the transportation network. And then this will have influence to the network level performance. So this one shows if I choose to repair these two bridges, this will kind of impact the traffic flow of users in this network. This is just an illustration. And in the service life of a structure or a structural system, this will be done over and over again. And the purpose of a decision maker is to find the right sequence of actions given the system performance so that the goal can be achieved. The goal will be minimization of the network level risk with the lowest cost. So this decision-making scenario in the life cycle that I mentioned before. So what you see here is just consider 5 generic actions for each bridge in a 10-year decision horizon for 100 bridges. So this is the number of potential policy pathways that you can have. So this is a gigantic number that you cannot really enumerate every one of them and then find the best policy. So that's why we must do things a little bit smarter. So one way to do this is to kind of abstract this decision-making scenario to this diagram that is usually used in dynamic programming or structural control. So here, that real-life system that will react based on the action you take is abstracted to a so-called environment. And the decision maker or decision-making tool is also called an agent. So the agent's tool is at each time step, it will choose an action and apply it to this environment. And that will change in the next time step, the state of that environment, meaning the conditions of all the bridges in the network, and will also incur a cost. So the flip of a cost is a reward. So in the jargon of reinforcement learning, this is also usually called reward. And those state and reward will be fed back to the agent, and then they can adjust their policies and then find a new action in the next time step to apply to this environment. So this is essentially a feedback control loop. Okay, so if that's the inspiration, so what we can do is, so if we are trying to find the best policy, optimize the policy, so we can first mathematically define what a policy is. That is a choice between based on the state of the system, the current state of system, and then find the best action to take. Okay, so you can define this policy pi in a probabilistic point of view. So given the state of the system, what will be the probability of taking different actions? And the purpose is, the goal is this recursive relation. That is, we want to find the best action to take at the current time step k+1 given the state S, so that we can maximize the cumulative value of those assets in this network. Okay, so this is just a recursive function. And here the reward at the current time step is defined based on both the asset level cost and risk and the network level cost and risk. So traditionally, you don't consider this second term. Okay, so of course, a different agency may have a different weight of how they want to emphasize the network level risk. So this is how we kind of mathematically formulate what is a policy and what is the function we are trying to improve. So with that out of the way, so some of the implications of that reward function is, if I set the weight of system level importance to 0, the network policy optimization become a asset level policy optimization. But this is not valid for an infrastructure system because the benefit of different assets is not linearly additive. So that, let's go back to this simple example with 5 bridges. So if you consider that 2 bridges fails, bridge B1 and bridge B3, so the loss of network capacity is 5. Okay, so, but if you only do it at the asset level with an additive performance measure. So you are likely to mistaken that network level consequences as the summation of bridge B1 fails and bridge B3 fails and add them together. In that case, that's 8 instead of 5. So that means you cannot really simply add all the assets together. So when you do the policy optimization, you have to consider the system state as a whole rather than simplify it to one specific element within that system. So that will create complications because we have a large number of structures in a system. So in each one will have a state. So you ended up having a really large state space. So in reinforcement learning, this is called the curse of dimensionalities. So the difficulties here is you cannot find a mapping for a policy for all the individual state of this system because there are so many different states because of there are so many different bridges in your network. Okay, so we need to find a smarter way to find to define a state-based policy. So that's where this deep reinforcement learning algorithm starts to take effect. So here we develop this so-called proximal policy optimization proximal policy optimization algorithm or PPO algorithm to formulate that optimization problem into a neural network. So you have the system state, you have part of the neural network that will tell you what will be the value of this state. And then you will have the part of the neural network tell you that what is the actions you need to take. Okay, so again, this value, one neural network is trying to approximate this value function. One neural network is trying to approximate this policy function. So it will be trained based on specific, based on the value laws and function laws that will not elaborate this too much. This is from basically the reinforcement learning method. So the purpose here is, so I'm going to, so this environment I showed here, this is in real life. It will not allow me to experiment and try different policies to see which one is the best, right? So what we can do is we can build a virtual environment and then build an automatic decision agent and then just let it try out different policies and then see which one gives me the most, the highest cumulative reward. That means the highest risk reduction. So the goal is with some algorithm as this experimentation process going on. So the total lifecycle cost, including the risk, will be reduced. Okay, so that will be done by the training of that neural network. And this is the algorithm specifics that includes gain experience. That is, let the neural network agent to just explore different policies in this virtual environment. And then you have this policy learning process, which is a smarter way of tweak my policies to improve it so that my total cost during this training process will be lower. And then that means I'm finding a better and better policy, right? So this is just an integration of this methodology that I just mentioned. I'll quickly skip through this to showcase this example that's we experimented with this methodology. This is the SUSFOX transportation network, which usually used as a benchmark in transportation engineering. So some of the assumptions we used is we consider all bridges are still good bridges, so they share the same deterioration relation. And we have the same assumption that link the condition to the failure probabilities of bridges. And we consider 5 generic actions for different state of the bridge. So here the policy optimization is conducted through training in 3,000 episodes in this virtual environment. So for bridges, 1 episode is the service life of that bridge, which is 75 years. So collectively, so we let this agent to experiment in 225,000 years of time. But it's virtual experiments, so each experiment is going very quickly. So that's why it's doable in a virtual environment. And the key thing here is to actually know the policy, understand the policy developed by this type of algorithm. So if we set the weight to 0, so this is the good old dynamic programming problem. You have 5 actions, 5 states, 5 actions, and then you have a best policy given different condition state. So condition state, I don't need to do anything. Condition 2, I need to do maintenance. Condition 5, I need to do repair. And over time, you will have this distribution of different condition states. Okay, so this is what has been put into bridge management systems at the asset level or at the element level. So this figure probably just shows you that the training process using our algorithm for different emphasis of the network level risk and for different case studies. So here, this first column in this chart shows you if I do care network risk, what will be the implications of doing just element level policies. So that means the policies will only depend on the condition state of the elements, but not consider what is the condition state of the neighboring bridges and the bridges of the entire network. So I just follow the same policy for all the bridges. Okay. So as you can see, this element level policy is not very effective because the long-term cost will increase based on how important you consider network level risk is. The other implication is, so with this really network level policy optimized through reinforcement learning, first, the long-term cost can be well controlled, and second, the actual cost is not that high. So meaning that I don't have to put into a lot of actual resources in order to improve the network level performance through this type of policy optimization. And the final question we want to answer is, the policy, as I presented before, is in the form of a neural network. So no sane decision maker will blindly follow a neural network without understanding it. So we do define a process to understand those policies that is transparent to human decision makers as well. So this slide shows the Monte Carlo results of the decision for different bridges given different condition state. So this is just a sanity check to see that, okay, my algorithm, when I set the network weight to 0, it gave me a reasonable element level policy that is consistent with dynamic programming results. And then we can also do the same kind of interpretation for other type of policies given different weights of network level emphasis. So here what you see is the change of policies. So here B1 and bridge B1 and bridge B1 and bridge B9 will start to take more stringent maintenance policies. This is because of their importance to the transportation network level performance. So the benefit of this approach is not only are we able to automatically identify the important bridge, but we can also come up with a policy that a bridge manager could follow. And if we further increase the importance of network level risk, we can discover that bridge B2 become more important as well. And bridge B9 will take an even further stringent policy. So by doing this Monte Carlo based policy interpretation, we are able to not only have a policy, but also to understand what those policies are. And then this type of policies can be understood by the decision maker and actually be input into the bridge management systems. So I will probably skip this. So this is the same concept that can also be used in a single structural system. So we can develop this adaptive maintenance campaigns for different bridge elements. And the benefit is we can lower the lifecycle cost of that bridge by about 20%, and kind of control the bridge failure risk as well. So in conclusion, so here at the system level, so we first, from this talk, I do want to convey this idea that is, so first we want to understand why to assess risk at the system level. So the fundamental reason is all the transportation assets are interconnected. So you have these rippling effects when one structure fails. And the second thing is the conventional preservation policies based on element level risk assessment may not give you the accurate risk assessment results, the risk values. That's the first part of the presentation. We see that the top 10 bridges ranked based on different indicators may differ drastically. So the second thing is, so we know the importance of doing asset level, doing system level risk assessment. Then how to manage system level risk, considering the fact that when we are doing system level risk assessment, the amount of system states explode really, really quickly as the network grows. So this is solved by this technique called deep reinforcement learning. So we will build a virtual environment for an agent to experiment and then find best policies over time. And then also present that policies in neural networks so that it can continuously improve the quality of the policies. And also, it is important to understand that policy represented by the neural networks through some in-depth analysis so that it can be understood by human decision makers and also be implemented in practice. So at last, if you only remember one thing from this presentation, it is fine with me as well. So that is, I think, the one key idea I want to convey is that risk of transportation structures and network should and could be managed at the system level. All right. So that's all from my presentation, and I'm happy to answer some of the questions. Thanks. So how are we going to do this? Yeah.
In the first paper, I'm wondering, what was the correlation between the network derived risk assessment and the project? How close could you get if you just had the project information and you were like a small DOT without the expertise to run a network?
Yeah, that's a really good question. That really depends on the topology of your network. So if you have, say, very closely connected networks, so the impact of individual assets will probably be intertwined with other things. On the other hand, if the connectivity is different, you will have a very loosely correlated performance correlation between project level risk and network level risk. So we did some numerical experimentation. So the key factors could be the average degrees of node degrees within your network. And it will also be dependent on the probabilities of failure of different links. It will also somewhat related to the adjacency matrix of your network. So it's a good directions to actually know what will be the fundamental driver of those correlations, but it's really network dependent. Yeah. Yeah.
Thank you.
Not too hard, right?
No. It's more conceptual. And I missed the first part of the presentation, but this is more like general and conceptual. In many cases, in dynamic programming, for example, adding discount rates are useful and help sometimes to find the optimal policy. And maybe you can comment on that. That's one thing. And how is that actually being implemented by DOTs in terms of discounting the future? And the other question that is a bit more conceptual is about this uncertainty about the input models, because sometimes these reliability models are probabilistic in nature, and kind of you are like a second order kind of uncertainty in terms of the future plus the uncertainty of the inputs. So how is that typically the state of the art in terms of DOTs adding this kind of subtle second order kind of uncertainties? And I guess it can be added to the framework, but maybe you can comment on that.
Thank you for the question. I'll answer as much as I can. So the first part is the interest rate. I think, I hope it's not too far. So here, this is the interest rate that you were referring to. So it is a very good question, because in reinforcement learning, the traditional applications such as robotics, so this is actually has a lot of effort going on how to quantify those discount rate. For asset management process, this is actually naturally occurring based on the real interest rate. The key difference I want to draw is the difference between nominal interest rate and real interest rate. You want to use the real interest rate to formulate this discount rate rather than the nominal one. Okay, so that's kind of why there are some difficulties of formulating this decision-making process as a reinforcement learning process, but there are some also advantages for asset management problems that does not appear in the traditional robotics applications for reinforcement learning. The second question is about the uncertainties. So you have the uncertainties within the system dynamics. That means how the system will deteriorate over time. That's, say, a MARKOV process. You have also the uncertainties of system performance. So here, two measures that or two comments I can have. So for the system performance, you can find non-simulation based approach to evaluate the risk at the system level. Okay, so one of the examples is the one that we proposed for the network level analysis. There are many other researchers do non-simulation based approach to get the risk reward function. So you don't have the oscillation because of the uncertainties within the reward function. The other thing is this type of comparison between a benchmark dynamic programming solution and a network solution to make sure that you are okay with whatever this neural network is giving you, and be kind of cognizant, but also be content with what the algorithm can do. So the reason I say that is, so this is the deep reinforcement learning results for different elements, but this is derived from that DRL, from the neural network. So you see that if my algorithm is perfect, it will all approach to the same element level policies. But this is not possible because of the dynamics, the uncertain dynamics within the system, as well as potentially future is the uncertainties in your reward function. So this is because, so the mean value of my reward is already very, very similar to the theoretical optimum. So my neural network cannot further improve the policy because of this inherent system dynamics, the uncertainties involved in the system dynamic. So that's why, I mean, this is the mean long-term cost is the value that I value the most. So what I'm saying, you need to be content with some of the results is, even though these are not perfect, but it should get work done. and it should give you the same similar long-term results. And also, once we do this type of policy interpretation, you can then see, okay, I'm going to manually adjust this to the other bridges so that it gives me a better policy. So I don't know at the concept level how this will be summarized, but I guess one is novel algorithms that reduce the uncertainties of your reward function. The other one is be aware of the goal of your application, and then be content with the results that you get, and then interpret it so that people are aware of the discrepancies. Yeah. So the DOT models are still based on element level. The dynamic programming results, as far as I know, of course, different agencies will develop their in-house best policies, but built in, let's say the Ashleware system used by DOT, there are built-in policies based on this element level results. But with the interpretation figures like this, rather than put into a neural network into the bridge management systems, you can inspect this neural network-based policy and then put this type of policies back into your Ashleware software. So that will be the end goal, I guess, how this will be and could be implemented in practice. Yeah. All right. Thank you. Thank you very much. Yeah.